I want to thank you for choosing this presentation to watch. If you're having any trouble with your electrical diagnostics, this just might be of some help for you as we take the mystery out of voltage drop testing. But before we begin, allow me to share a short video clip with you. Pay attention to what you see. If you work on cars for a living, you've probably taken this measurement at least 1,000 times. Positive meter lead of a meter on the positive post of the battery, negative meter lead on the negative post, and you're not going to be too surprised when you get a measurement like the one here. But what if now I take the positive meter lead and put it on a body ground, like here, and I get a reading like this one? Now wait a minute. Negative meter lead is on the negative battery post. Positive meter lead is on a ground. How am I reading voltage? Did you notice where I placed the leads of my meter? The negative meter lead is connected to the negative battery post. The positive meter lead is attached to a body ground in the engine compartment. Now let's see here. The key is on, but the engine is not running. Both of my meter leads are on a ground point, but the meter is still reading voltage. Now, if you know why we can read voltage on the meter when apparently both of my meter leads are attached to grounds, then you can still watch this video and get some refresher training or move on to another topic. But if you hesitated though, or you find yourself in a total state of confusion, wondering how the heck I'm reading voltage when logic seems to tell me I shouldn't be, and most importantly, why there's a voltage reading on my meter at all, well, rest assured, you're not alone. Even today, troubleshooting electrical problems seems to be one of the biggest challenges technicians face. I've made similar presentations all across the country over the last 10 years, and still we get requests for articles, videos, and webcasts on this very subject. And it's no wonder. The automobile today is nothing like the one I cut my teeth on, with more and more systems being electrified. And then, of course, there are the rolling networks that these vehicles have become, with dozens of computers responsible for overseeing everything from engine management to what radio station you're listening to, all communicating with each other, even the outside world. There is no doubt that we are moving to an electric future, and your ability to diagnose and repair these electrical systems will directly impact your ability to earn a good living. The good news is that the underlying principles of electricity haven't changed. It doesn't matter whether you're troubleshooting a failed headlight on a classic Mustang or testing the power and ground circuits on a forward-facing radar assembly. They are both electrical loads, and both circuits have to flow the right amount of current in order for either to work properly. So why do so many of us still struggle with electrical concerns? I think I'm pretty qualified to answer this question, and it only has a little to do with my role with Motor Age over the last 10 years. Before getting the opportunity to join Motor Age, I was a working technician just like many of you. And the last place that I worked was a nice place to work. I really enjoyed it there. And one thing that stood out for me was that the very first year I was there was an internal technician competition. Well, I thought that was pretty cool. I figured, what the heck, I'll give it a shot. Well, I made it to the finals, and it was held at a national level for this particular employer. Got to the contest, very confident. Very first challenge was a written test. Nailed that, knocked that out of the park. Then there were a number of workstations. We had to perform a variety of tasks related to automotive repair. No problem there, knocked that one out of the park. And now I'm really confident I got a shot of taking this thing home. Well, the very last challenge was a timed troubleshooting challenge, and of course it had to be an electrical one. I'll never forget that night. The vehicle was a GMC with a MAF circuit code. I don't recall exactly which one it was, But I did know that this new test I've been reading about would be just the ticket for solving this problem quick and easy. It was called voltage drop testing, and I knew the how of the test. I knew where to place my voltmeter leads, and I knew what scale to use. But I didn't speak the meter's language. When it provided a reading, just like the one I showed you, I couldn't interpret what it meant. And one of my judges on this station, God bless him, he tried to steer me in the right direction, but the more I struggled, the more I locked up mentally, and the worse it got. Well, needless to say, I didn't win the competition, and I was really ticked off at myself because it was my contest to win or lose. You know, the reason I didn't win was very simple. In hindsight, the foundation of fundamentals that I had was weak, and I've found since then that the same is true of many technicians around the country. We have to shore up that foundation before we can build anything upon it. So when I got back to the shop, I took a battery, some wire, and a few light bulbs, and I built this very simple circuit. I took my meter and I started measuring at different points along the circuit, taking the time to learn what each reading was trying to tell me until it suddenly became so simple. And that's exactly what I wish for you in this video presentation. If troubleshooting electrical concerns is a challenge, pay very close attention to what I'm going to share with you today. Review it as many times as you need until you make it your own. But, and here's the really important part, you're also going to have to practice. You're going to have to take these skills that I'm demonstrating and try them for yourself and repeat it over and over until you too have that aha moment. So what does it take to become a better electrical troubleshooter? You have to have a solid understanding of the fundamentals, as I've already shared. That's true whether you're attempting to solve electrical problems, drivability problems, or any kind of problem that you're faced with on the car. You have to master the basics. And I know how most of you feel when any presenter talks about basics, but let me challenge you with this. Consider your favorite sports team. Before the season starts, there is usually a preseason training camp for the team, isn't there? And what do they practice? Fundamentals. With a solid foundation in the fundamentals, they can build on the more advanced skills of their chosen profession. And as a tech, you can do the same. It also makes it easier to handle the next step in becoming a successful electrical diagnostician. Like any other system on the car, to successfully isolate the cause of a problem, you have to take the time to understand exactly how the circuit that has the problem functions. What source of information do we have that provides that information? That's right, the wiring diagram. If you want to be good at solving electrical problems, you have to be comfortable reading and interpreting a wiring schematic. It's not enough to be able to trace a wire from point A to point B. You have to be comfortable that you're able to determine what's going on in those components. One of the best classes out there is offered by a good friend, George Menchu of AES Wave. If you ever have a chance to attend his class, I strongly encourage you to do so. If you can't make it to one of his live sessions, you can get the next best thing. The article he wrote when he first introduced his concept, along with a full-size poster that outlines the technique for you. It's available at aeswave.com. I also encourage you to take advantage of the library available to you as part of your admission to this event, and to check out our other resources, the Motor Age Training Connect platform, and of course, Motor Age Magazine on YouTube. Next on the list of to-do items is to become comfortable with the tools you'll use in your diagnosis. For nearly every test you'll ever need to make, your digital volt-o-meter will work, but there will be times when a simple test light will do, and there will be times when you'll need the power of a scope to isolate the problem. Do you own or use a scope today? You may want to consider adding one to your tool arsenal. There are scopes out there for every budget, but if you try real hard, maybe the boss will buy it for the shop. Now, let's shore up those fundamentals. No matter where you first learned about electrical troubleshooting, odds are that there are gaps that you've kind of filled in for yourself. I know I did, and it cost me, as I shared earlier. So let's start by establishing a comparison, a frame of reference of sorts that I know you are all familiar with, the basic 4-cycle intake stroke. We all understand that as the piston moves down on the intake stroke, the volume in the cylinder increases. And we all understand what happens to the pressure in the cylinder as the piston descends, don't we? We learned it back in 7th grade science class. It's called Boyle's law, and it states that at a constant temperature, the volume of a given mass of a dry gas is inversely proportional to its pressure. And that just simply means that the pressure in the cylinder is going down as the volume uncovered by the descending piston goes up. And since that pressure is less than atmospheric, we consider that low pressure a vacuum, don't we? But the vacuum in the cylinder is short-lived, isn't it? Why? Well, the intake valve opens. So what? As the pressure in the cylinder drops below the pressure that is in the intake manifold, the higher pressure in the intake manifold will force air into the cylinder until the intake valve closes or the pressure equalizes. That's kind of how the battery works if you think about it. The chemical reactions in the battery causes a buildup of electrons at the anode. This is our high pressure area, just like the one in the intake manifold. The other end of the battery is the cathode. Here, there are very few electrons present. That's our low pressure area. Again, just like the one in the cylinder. The problem is there's no path between the two, no way for the high pressure to get to the low pressure. The electrolyte keeps the electrons from going straight from the anode to the cathode within the battery. However, if we put a wire to connect the cathode and anode, the electrons will be able to get to the low pressure side, as anyone that's ever shorted 2 battery posts together can certainly testify to. So to summarize so far, airflow into the engine is caused by the pressure differential between the outside air pressure and the intake pressure. Flow is limited by the restriction caused by the throttle plate. So how do we measure the pressure differential? Ever hear of MAP, or manifold absolute pressure? The MAP sensor is measuring the absolute pressure in the intake manifold, isn't it? That's the difference between the pressure outside the engine and the pressure inside. For example, if the outside pressure, or what we know as barometric pressure, for your area is 14.7 psi, and the intake manifold vacuum as measured with your vacuum gauge is 20 inches of mercury, that's roughly 10 psi. When you look at the MAP PID on your scan tool, you should expect it to read about 5 psi, the pressure differential, the absolute pressure. Measuring voltage is very similar. When you measure the voltage in a battery, you aren't measuring a static number, a quantity, if you will. You are measuring the pressure differential between the 2 battery posts. Let me see if I can make this concept just as clear as I can, because it's very important to understand this. 1 meter lead is attached to a 0 voltage potential, while the other meter lead is attached to a 12.6 voltage potential. That's on a fully charged battery, of course. And the difference between the two is what you see displayed on the meter's screen, 12.6. Now let's talk a little bit about current flow. Conventional theory is used to build your test equipment. And that theory says that the positive battery terminal is the one with the abundance of electrons, the high pressure side, if you will. And the flow is from positive to negative. In that case, your positive meter lead is attached to a 12.6 voltage potential, and your negative meter lead is attached to a 0 volt potential. But we now know that isn't true. In actuality, electrons are negatively charged, and the abundance of free electrons is at the negative battery terminal, not the positive. No matter, when we place our leads in reverse, we'll get a similar measurement, except now we'll have a negative or minus sign in front of the reading. Now, do we care which way current flows? Not at all. It doesn't matter how you think of this. Just remember this one critical point. Your voltmeter is measuring the difference in electrical potential, that's pressure, between its leads. Now let's move back to our intake stroke for a moment. What is the limiting factor to just how much air makes it into the cylinder? Well, that would be the position of the throttle plate, wouldn't it? The throttle plate restricts airflow from outside of the engine into the intake manifold and ultimately to the individual cylinders. When the throttle plate is wide open, there's no restriction to flow, no resistance, and the flow of air molecules will go as fast as they can to fill the low pressure in the intake. To slow that airflow down and as a result control engine speed, we close the throttle plate so it's barely open. Well, that sounds like a source of high resistance, doesn't it? The result is lower airflow. We measure that in terms of grams per second. So how does that relate to electrical flow? The restriction to flow caused by the throttle plate is similar to the restriction to electron flow that would be caused by any source of electrical resistance. And the grams per second that we're measuring is similar to measuring electron movement in an electrical circuit, only there we call it current flow, and it's measured in units called amperage. And our good friend, George Ohm, he describes this relationship very well in both cases. Ohm's law has been hammered on in nearly every electrical class I've ever attended. And why? Because it clearly explains the relationship between voltage, resistance, and current flow. Now I want you to make a note and I want you to plant this firmly in your brain. For a constant voltage, an increase in resistance results in a decrease in current flow. The reverse is also true. For a constant voltage, a decrease in resistance results in an increase in current flow. Remember the wire connecting the two battery posts and why the wire would fry as soon as the contact was made? That's because there was no resistance to current flow, so the high pressure of electrons at the negative post hauled booty to fill the low pressure side at the positive battery post. And that high current flow also results in high heat, enough to fry the small gauge wire almost immediately. So how do we regulate current flow to avoid frying wires? Well, the only reason we need electrical circuits in the vehicle in the first place is to perform some kind of function. That might be to illuminate the road ahead, to keep the windshield clear when it's raining, or to ignite the spark plugs and open the injectors, or any one of 1,000 other functions that electrical circuits perform today. And at the heart of each is the device that's responsible for performing that task, what we call generically the load. And the amount of work the load has to handle will determine how much current it will need to do so. For example, it doesn't take much effort to pull a door lock down, but it takes a lot of energy to turn the engine through to get it started. The load is the primary factor in how much current will flow in the circuit. Now let's cover this here as well. Everything that goes into making up an electrical circuit, and we'll go through them shortly, offers some amount of resistance to electrical flow. But relative to the load, it's minute. The load is and should be the only real source of the resistance in the circuit. You may want to repeat that to yourself one more time. Now, the battery is the source of differential electrical pressure, measured in volts, that is needed to get electrons to flow. But in order for them to start flowing, we have to connect the two sides of the battery. We have to have a complete path for the electrons to follow. The electrons themselves are the carriers of the electrical energy we want to harness to perform some kind of task or function. That is, to operate some form of electrical load, a light bulb, a motor, an ignition coil, or an ECU, or any of 1,000 different other devices. And if we place a load in between the two battery posts and make the appropriate connections at either end, the load will work, won't it? And that is a basic electrical circuit. The only problem is we can't control when the load works. In this case, it would stay on until the energy in the battery is depleted. So we need some way to control the circuit, and that's what any component that opens or closes the circuit path is called. It includes mechanical switches, electronic drivers, and relays. The control device can be located on either side of the load. Now let me clarify what we're talking about here. The section of the circuit path located between the positive post of the battery and the load is referenced as the positive side of the circuit, while the section of the circuit path between the ground terminal of the battery and the load is referenced as the ground side of the circuit. You may also have heard references to high side drivers and ground side drivers, where high side is referencing the positive side of the circuit. In this case, a high side control is responsible for completing the path between the battery and the load, and we often say that it provides voltage to the component, though that's not entirely accurate. Why? Well, I want you to get rid of the notion that electrons flow like water from a spigot. Electron flow travels at the speed of light. It's, for all practical purposes, instantaneous. So the only reason for us to understand what side the control device is to aid us in our troubleshooting. And I'll demonstrate that a little bit later in the presentation. We also need to protect the circuits in the vehicle in the event of real-world problems that could cause the circuit to be interrupted. Now, if the circuit goes open, electrons can't flow and the load won't work, but the circuit won't be damaged further as a result. However, if the circuit is broken on the positive side of the circuit path and then comes into contact with anything that will allow the path back to the battery to be completed, well, that of course is a short to ground, and we all know just how quickly damage to the wiring harness will occur. To avoid that possibility as much as we can, we need some form of circuit protection device, a fuse, a fusible link, or circuit breaker. Some electronic control units have circuit protection built into them. And one thing to remember when it comes to most of these devices, most are thermal protection devices. That is, they react to the amount of heat generated by the current flowing through them. Ever deal with an intermittent blown fuse complaint? So to review, every electrical circuit has to have the following elements: a source, a battery typically, sometimes the vehicle alternator, a load or device that's actually doing the work in the circuit, a control device that allows us to turn the circuit on or off, a circuit protection device, a fuse, a fusible link, or circuit breaker, and finally, a complete path that connects it all. Unless there's a complete path, the circuit's not going to work. Okay, I think we're up to speed on what makes up a fundamental electrical circuit. I think we also understand now that current flow is impacted by the amount of resistance in that circuit. If resistance goes up, current flow goes down, and vice versa. If resistance goes down, current flow goes up. We also know that everything in the circuit has some measure of resistance to it, but the load, the device that's doing the work, should be the only real source of resistance, the primary source of resistance in the circuit that we're working on. So what can go wrong with an electrical circuit? Well, in my opinion, there are 5 failure modes, and I want you to keep them in mind when you're troubleshooting a problem. First is the open circuit. That is, there isn't a complete path for the electrons to follow. Number 2 is the short circuit. And technicians who use this term are typically thinking of a short circuit to ground. A short to ground occurs when any portion of the circuit path completes the path to the negative side of the battery before its intended point. And this fault can have different effects, depending on where exactly the fault is occurring. Knowing these can help pinpoint exactly where the fault may be. The first possibility is if the circuit path connects to ground on the positive side of the circuit, but before the circuit protection device or any high side control device, in which case the wiring will overheat and melt. The next possibility is if the circuit path connects to ground on the positive side of the circuit, but after the circuit protection device and before the high side control device. The fuse should protect the wiring and melt, resulting in a now open circuit condition. The next possibility is if the circuit path connects to ground on the positive side of the circuit after the fuse and after the high side control device. The fuse should protect the wiring and melt, but only after the circuit is turned on. And of course, that will result in a new open circuit condition. Next, if the circuit path connects to ground on the ground side of the circuit, but before any ground side control, the circuit will be on even when the control device is turned off. And finally, if the circuit path connects to ground on the ground side of the circuit, but after any ground side control device, there will be no effect on the circuit operation except for that caused by variations in resistance. And we're going to get to that in a moment. Number 3 is the short circuit to power. This is not as common as it used to be and occurs when a hot power feed's bare wire comes into contact with a cold power feed of another circuit, and it's after that circuit's control device. Now, of course, we have to include load failure as a possibility. And while it's not strictly an electrical fault, it's commonly overlooked as a potential cause. For example, an air conditioning clutch compressor that won't engage. It's getting voltage and ground currents flowing, but it won't engage because of a mechanical failure of the clutch assembly. Maybe just an air gap that's too large. Another example is a fuel injector that electrically is just fine, but mechanically it's stuck open or closed. And how about one more? A fuel pump that isn't pumping enough gas. Electrically it seems to be fine, but the rotor is seizing in the case because of a failed bearing, or it's trying to push against a restricted fuel filter. So don't overlook these kinds of possibilities or get tunnel vision during your diagnosis. And I saved the best for last, high resistance. I could say here that nearly every electrical problem is related to some change in the circuit's resistance. After all, an open circuit is certainly a change, as is a short to ground. But the most common cause of electrical problems that you're going to face, and also one of the more frustrating to find, is when excessive resistance occurs in the circuit. Now remember, we said that everything in the circuit has some kind of resistance. Everything has something to offer and add to the total on the circuit. But the majority of those things are minor in nature that we really don't have to worry about them. It's the load that is the primary source of resistance in the circuit. And again, all of these are designed in. We know that's going to occur, so they're not the problem. It's when an unwanted outside source of resistance creeps its way into our circuit. The thief, if you will, that's there to steal voltage potential away from the load that we want to do the work. What do these thieves look like? Corrosion is a big one. Loose or damaged ground connectors is another common source of unintended resistance. So are damaged connectors. I once had a GM factory trainer tell me that it's GM's view that any connector that has been opened or closed more than 3 times is worn out. Imagine the impact on the connector from improper testing techniques. You know, that one guy that shoved his multimeter probe into the connector end. And now for the really important part. How do we find, troubleshoot, and fix the thing? Chafed wiring, corrosion, and similar sources of resistance are visible, but there are other causes of resistance that are not. Consider a loose ground connection or an excessive gap in a connector block. all make it more difficult for current to flow, but not all of them can be found using simple visual or even static testing methods. We need to test the circuit dynamically to find the thief. Consider this example as another plug for dynamic versus static testing. You know almost intuitively that if you measure the resistance of a single strand of wire, it will be close to 0 ohms. You also know that if you perform the same measurement on a length of battery cable, it will likely measure about the same, close to 0 ohms. Well, if they have the same resistance, then why do we need such a big cable for the starter motor, but use smaller wiring for nearly everything else on the vehicle? Again, you know that the current demanded by the starter is a lot more than what's required by a light bulb. The smaller wire can't handle that load. So that rules out static resistance tests as a definitive way for testing the ability of a circuit to carry its current load, doesn't it? Now, when you're faced with a diagnostic problem, let's say a DTC that you've never encountered before, what do? How many of you grab the diagnostic flow chart out of your service information source of choice and start testing from the top? Or do you read up on the DTC itself to learn how it sets and how the ECU involved tests for the problem, and based on that, design your own test procedures? I tend to favor the latter. I see no sense in blindly performing tests when I don't know what or why I'm performing those tests. Agreed? So let's apply that same diagnostic approach to our electrical concern. The very first thing we have to do is grab a schematic and understand how the circuit is supposed to work. And then we can compare that to how it is or isn't working. Let's start with something relatively simple, a center brake light that isn't working. The vehicle is a 2014 Scion TC, in case you want to follow along. Let's take a look at the exterior lights diagram and see what we can learn about how this circuit functions. Now, when I'm reviewing a wiring diagram, the first step I take is to identify the load that has the problem, so let's find that first. Once I have the load identified, I move on to isolating the ground path back to the battery and then the power path back to the battery. If I have a source, a load, a complete path between the two, the load should work, right? Now, the ground on this style of diagram is usually easy to isolate, so let's start there. It's easy to see that the center brake light is grounded through the junction connector L11 to the body ground point L1 in the rear cargo area. Now, what else shares this ground? The two license plate bulbs do, but the key thing for me here is that the other two brake lights do not. Take a quick look over to the left of the same diagram. The two main stop lamps, as well as the turn signals and tail lights, are grounded through junction connector H21, the same one that brings the power in, and ends at body ground H2 under the left side quarter panel. That makes L11 unique to the center brake light. Keep that in mind. Now on to the power side. With only one wire left on the center brake light connector, the power side has to be coming in on the yellow wire. Let's trace it all the way back to the battery to see if we can find the remaining elements of a typical circuit. Remember what they are? I still want to find the circuit protection device and the control device while I'm completing the path from and back to the battery. The yellow wire leads to a noise filter, a capacitor, where the wire color changes to blue. Continuing from there, we see it leads to a junction connector H21, the same one carrying the grounds and power for the main stop lamps, but turning to pink before it gets there. There are 4 wires sharing that junction. One has to be going back to the battery, so let's find out which one. Since most block diagrams are usually arranged with power toward the top and ground toward the bottom, I'm going to pick the light blue wire next. Now this leads to a junction block at the instrument panel, and it's easy to see that the light green it's connected to is headed towards the ECM. Think we're on the right path so far? Why would the ECM be involved in this circuit? It's not engine management. It's not emissions related. Let's keep going for now. If we follow the path through the ECM, we see it comes to the stoplight switch. But this switch is showing that the black wire we're now on is connected to the red wire when the switch is not, for lack of a better description, active. Okay, what about the other side of the switch? There we have a blue wire going back to the same junction block our light blue wire ended, and a gray wire leading back to a fuse labeled stop fuse. Okay, regardless of the ECM's role at this point, I think we found our way back to the positive side of the battery. And we've also identified the control and the circuit protection used in this circuit. Notice the fuse is labeled hot at all times, so we know that it isn't dependent on the key being in any specific position. The brakes should illuminate whenever I touch the brake pedal. If needed, I can use the power distribution diagrams to complete the rest of the path back to the battery. Is this power supply path unique to the center brake light when compared to all of the brake lights? Well, up to a point, yes. Let's follow it in the other direction and see where it becomes unique to the center brake light alone. The positive side of the center brake light circuit starts at the battery and enters the stop fuse. From there, it passes to the stop switch assembly. When the pedal is depressed, the switch, normally open, closes and completes the overall circuit path. That's our control. It leaves from the switch on a blue wire and leaves the instrument panel junction block on a light blue wire. That brings it to junction connector H21, and here the path to the center brake light is unique. Everything up to this point is shared with the two main stop lights. So if this brake light were not working, what would be one of the first things you did? I'm betting a lot of you would consider trying a new bulb first. Well, that's not so easy if it's an LED strip. We don't usually have those lying around. Besides, why shotgun a part at it? What if that isn't it? Another possibility is to inspect the operation of any related load. In this case, what are the other brake lights doing? What about the license plate lights? Remember, they share something with the center brake light as well. What if the other brake lights worked, but the license plate lights didn't? What would you suspect is the cause? If none of the brake lights worked, but the license plate lights did, then where would you go? And if all of them worked, then what? If you take a little time to review the wiring diagram and look at the symptoms, you'll save yourself a lot of time avoiding testing the unnecessary. Now, armed with some ideas on where the problem is going to be, it's time to narrow it down even further. Does the absence of the light indicate an open circuit somewhere? Not necessarily. Let's perform some tests. What would you do next? Well, if you said you would disconnect the center brake light and see if there were 12 volts at the connector, what does that really tell you? All that tells you is that the difference in voltage potential is with no load and no demand on the path. That's just open circuit voltage, and they should be exactly the same as you would measure as if you measured directly at the battery. It's a static test, and it tells you absolutely nothing. So instead, let's test it dynamically while it's working. Why? Because the role of voltage is to overcome the resistances in the circuit so electrons can flow. According to a guy named Kirchhoff, all available voltage will be used to overcome all of the available resistance so that electrons can do just that. Let's try that again. All available voltage will be used to overcome the resistance of the circuit. One more time. all available voltage will be used to overcome the resistance of the circuit. I really want you to remember this principle. So let's look at it a little closer. Voltage is used to overcome resistance so electrons will flow, and according to this principle, all of it will be consumed by that resistance. The thing is, there's more than one source of resistance in a circuit, isn't there? We learned that everything in the circuit offers some resistance: the wiring, the connections, the switch contacts, even the fuse, all offer some resistance. And according to this principle, some voltage will be needed to overcome each and every one of them. The amount each will use is going to be in proportion to the amount of resistance each offers overall. Keep that in mind. We're going to explore that more deeply in a moment. Do you remember what we said should be the only real source of resistance? That's right, the load. The load is the primary source of resistance. It's the one component that regulates the current flow in the circuit, and all the others pale by comparison. So if that's the case, shouldn't this statement be true? The majority of the available voltage should be going to the load, and after the voltage has done its job there should be very little left over. Think of it this way. If voltage is indeed a measure of the difference in potential between the meter leads, if we look for the potential present before the load, what should we expect to see? Nearly full potential. And once that potential has been consumed, used to overcome the resistance and allow electron flow through the load, what should the potential be on the other side? Nearly nothing. So I want to make sure you understand this. When we check for voltage potential on the positive side of the load, we should measure close to, but not exactly, source voltage. And when we move the meter lead to the ground side of the load, we should measure close to zero, but not exactly zero. It will never be perfect either way. The reason is that there are all kinds of little sources of resistance still present on both sides of the circuit, and as we learn in Kirchhoff's law, they still want to get their tiny little fair share. And what if the circuit is not working as it should? Remember circuit fault number 5? Increased resistance in the circuit. In this case, we're looking for unwanted sources of resistance, and it doesn't take much. Even a small amount can affect the operation of the load. Now, we really want to go into this because this is critical to your future success in troubleshooting electrical problems. Now, let me stress one more time, this is a dynamic test. The circuit you're testing must be on and current must be flowing when this test is being performed. If current's not flowing, then there's no voltage being used. There's no change in electromotive potential, and therefore there's nothing worth measuring. Now take a look at this simple diagram. If one resistor has 10 ohms of resistance and we measure the drop in pressure or voltage across it, we'll get nearly source voltage at the positive side of the resistor and almost a perfect zero on the other side of the resistor, again when the circuit is closed and current is flowing. This change in pressure, potential, across the resistor, this drop, well, that's voltage drop. Earlier I mentioned this guy named Kirchhoff. Kirchhoff's voltage law is actually stated as V equals V1 plus V2 plus V3, or applied voltage equals the sum of all voltage drops, or the source voltage is equal to the sum of all voltage drops. Now in this case, we're only identifying one voltage drop, the drop across the 10 ohm resistor. Let's go back to our malfunctioning center brake light. If I place my negative meter lead on the negative post of the battery and use my positive meter lead to measure the electromotive potential, the difference between potential between my meter leads, between the battery and the positive side of the brake light, what should I expect to see? Ideally, source voltage. But in reality, we're going to fall a little short of that, maybe a few tenths or so. Why? Everything in the circuit has some amount of resistance. All are significantly less than the load, but it's resistance nonetheless. So any minor variances can be accounted for by these sources. Now, to keep it easy, let's add a second 10 ohm resistor in series with the first. What do you think will happen when we go down the line and take our measurements? Since the resistors are equal, we should expect that the voltage consumed by each will also be equal. Now think of the resistance, the resistor on the left, as the load. That's the resistance that's supposed to be there. And think of the other one, the one on the right, as our thief, the unwanted source of resistance, somewhere in the circuit. Maybe a corroded or damaged connector, loose ground connection, something. At the first resistor, we should still measure the source voltage we started with, just as we did earlier. Now, moving to the ground side of the first resistor, we'll now measure roughly half of the source voltage. That's because the voltage is now being shared between the two major sources of resistance, just as the rule we just learned explained. Remember the example I shared in that short little video clip right at the very beginning of this presentation? Now we've moved our lead and we're measuring on the ground side of the first resistor. We should expect to see near 0 volts, shouldn't we? All voltage applied will be consumed by all sources of resistance in the circuit proportionally. Read that again. All voltage applied will be consumed by all sources of resistance in the circuit proportionally. So the presence of voltage indicates that there's an additional resistance to overcome. We know we have one here, but what if we were measuring this on a vehicle? Wouldn't that tell you there's a problem yet to be found? So moving on, with no other major sources of resistance between the ground side of the first resistor and the positive side of the second, we should read the same amount of electromotive potential here. And finally, when we pass on to the ground side of the second resistor, our reading should be the same as we saw on the ground side of the first time around, nearly a perfect 0. Nearly, not quite. Nearly. Because all of the voltage has been consumed now by all the sources of resistance in the circuit proportionally. And that's exactly how we're going to find where the unwanted source of resistance is hiding in the circuits on the vehicle. I cannot stress this concept enough. How does the unintended source of resistance impact the circuit? Remember what Ohm's law has to say about the relationship between voltage and current flow? If voltage decreases, current flow decreases. Think a moment about the 2 resistor circuit. We had just over 12 volts going in, but is that how much voltage that was actually being applied to each resistor? We can use what we learned about using our voltmeter to answer that question. Remember how the voltmeter works? It measures the electromotive potential, the potential difference between its leads. That's voltage. If we place our leads just across the resistor, what do you think we'll measure? So that means that the bulb only got about 6 volts or so rather than the 12 it needs to work correctly. What's the result? Dim bulb for sure. Now, is that actually caused by low voltage? Not directly. The lower applied voltage was caused by the addition of resistance to the entire circuit. That second resistor wants its fair share of the total, and that means lower current flow. And that's why the bulb is dim, or the motor spins slowly, or the injector doesn't open. Are you starting to understand where we're going with this? All right, so let's move this application of theory into something that's more real world. And you can see I've got a simple circuit diagram here on the board. Let's just say your customer comes in with a complaint, something's not working electrically. Now I like to use a bulb circuit as a learning aid because it's easy to see when it's not working right. We've got a bright burning bulb, so we should think that pretty much everything's okay here in the circuit. Now, when your customer presents you this problem, I want you to take your first of 3 measurements, okay? The very first one I want you to take is at the battery. Let's see how much source voltage, how much voltage potential, how much electromotive pressure potential that we have. So we'll measure it with our voltmeter. Right now I'm showing a little over 12 volts on the meter. Now once I know what that number is, I'm going to take the second of my 3 measurements. And I'm going to move my positive meter lead to the positive side of the load as close as I can get it. It's key to leave the negative meter lead at the battery and get as close to the load as you can in order to test as much of the circuit path on that side of the circuit as we can. Remember, I can only measure the potential between my 2 meter leads, and that's what we're doing here. So here I'm measuring about 11.9. Earlier we were at about 12 volts. That's only about 1/10 of a volt difference, okay? It's not exactly the same, is it? Do you remember what I told you why it would not be exactly the same as what we measured at the battery? Because all of the rest of this has some resistance. It's minute, it's not much, but it's there. And according to old Kirchhoff, all of them are going to get their fair share. Might be a small amount, but they're still going to take their fair share. So after everybody here has gotten what they wanted, I've got 11.89 volts left to push electrons through my load. So far, so good. Now, third measurement. We're now going to take the positive meter lead and we're going to move it over to the ground side of the load. Again, as close as we can get, leaving the negative meter lead referenced at the negative post of the battery. What reading do we get? About 150 millivolts. That's only about 0.15 of a volt. Again, not much. But why isn't it a perfect 0? Well, again, everything from here back to the battery is waiting for its fair share. Everything here has some amount of resistance. Not much, a little tiny, but nonetheless, it's still going to take its fair share away from the total. All right, so everybody with me so far? So far, I've been able to check the electrical integrity of this entire circuit. I've got good battery voltage. I have very little loss going to the load. I have very little, I'm showing that the load is being consumed, right? The voltage is being consumed by the load. Very little left over. So that means this path is good. That path is good. The load appears to be good. Nothing wrong with this circuit. Now what do you say we put a bug in it and see what we can learn using this same testing approach? All right, so now for our next example, we have a load that is not working. How many of you, honestly, when you have a light bulb in a vehicle that's not working, the very first thing you do is throw a light bulb in it. And then you start scratching your head when it still doesn't work, right? Maybe you go check the fuses, you just start kind of shooting in the dark. Let's follow the testing method that I just shared with you, and we can find out where this is occurring, where the problem is occurring. So, first thing we do, measure the battery voltage. In this case, we're starting with 12.3, 12.4. That's a good decent number. I'm good with that. Second step was what? We're going to move our meter lead now to the positive side of the load. What do we read now? I mean, it's almost 0. In fact, it's bouncing around. Have you ever seen your voltmeter bounce around like this? Really can't settle down on a number? When does that happen? when your meter leads aren't connected. Can you see that? And if they're not connected, there's no complete path, is there? What is that telling me? Must have an open. So as a side note, you want to make sure your meter leads are okay before you even start testing. Just put the two together and it should stabilize at a perfect 0. All right? All right, so let's go back to where we were. So now we have ghost voltage. That's telling me that there's an open circuit somewhere between the positive side of the battery and my light bulb, right? So how do I find it? Well, we're going to start working our way back until our meter reading returns to normal. So let's just move back here. We'll come to this side of the fuse. Still reading the same. Come to the other side of the fuse. Still reading the same. And we're just going to work our way back until we get to where we get the same meter reading that we expect to see. And what is it we expect to see using this method? Pretty close to source voltage, right? Still haven't gotten there. All right, now we're there, 12.43 volts. So somewhere between these two test points, here and here, is where the break lies. So this is how you find it once you determine which side of the circuit has the problem. Okay, I kind of feel like that movie Wayne's World as we go from one example to the other. Not a lot of division between scenes, right? Just go boom, boom, boom. Maybe I'll put that in there just for fun. Anyway, let's go on to our next example. Again, symptoms the same. We have a light bulb that isn't working. Is it the light bulb? I don't know. But I think by now you understand I can take 3 measurements and gauge the health of this electrical circuit pretty easily, right? So let's go ahead and we're going to do that. First one, of course, is at the battery. 12.48 volts is what I'm measuring here in this case. Next step is to what? Take that positive meter lead, get as close to the load as I can, take measurement number 2. Well, here we got 12.48 volts. That's exactly the same as I had there. That's a perfect 0 difference, isn't it? Perfect 0 voltage drop. And I know that's just not possible in the real world. All of these items along the way have some resistance that they're putting in this circuit. All of them are going to want their fair share. Maybe just a little, but they're going to want their fair share. And nobody's taking any of it. So that means no voltage drop is occurring. And it's only one way that's going to happen. There's no current flowing. Current's not flowing. If the circuit's not closed, there can be no voltage drop. So either I have an open circuit or I have not turned the circuit on. Now, where's the open circuit? Well, do I have potential at the positive side of the load? Yeah. So it's not that side. Remember what we saw when the open was on the positive side? Ghost voltage, clearly an open circuit. How do I find out? Just like before, we take that third measurement. There you go. It's the exact same. So I know it's not in the load. It's got to be between here and the battery. All right, here's another example for you. Once again, same symptom, bulb's not working. Where's the problem? 3 steps to know, right? 3 steps I can tell what side of the circuit has the problem. Number 1, battery voltage. We have that measured, 12.4 volts. Next step, what? Yes, indeed, just like always, we're going to move that positive lead right up to the battery, positive side of the load as close as we can get. And there you got, same voltage, just exactly the same thing we just saw. So what do you automatically know right now? I'm dealing with an open circuit and it's got to be between either the load or the ground side. So what we do next, we take that third measurement. Come over to the ground side. And there you see ghost voltage. So now I know that there's an open circuit between this test point and this test point. It's only one thing there. Got to be the bulb, the connector, anywhere from here through the filament and back out the other side. Somewhere in there, there's an open circuit. Now, as I mentioned earlier, there's something I want to really quick throw in here. If we check the circuit and we get normal readings like we did in the very first example, everything tests just fine, but the light is still not working or the load is not working, and this is going to be mainly like mechanical devices, fuel pumps, fuel injectors, things of this nature, then it could be a mechanical problem. If electrically it tests fine, but it's still not working or working properly, then it's got to be something mechanical with that component. Just don't overlook that possibility when you're doing your troubleshooting. Now, finding the open circuit, that's usually not the hardest part about electrical problems that will come into your shop. This is one that can drive you crazy and make you frustrated. It's something where it's on, but it's just not working the way it should. Dim light bulb, a blower fan that's running slower than it should, things of this nature. And it's all because there's a change in the current flow going to the load. It's not getting what it needs to work. That's the bottom line. Can we still find it using this method? Yes. In fact, this is going to be the easiest method to use to find the cause of problems like this. We can check the integrity of the entire circuit in 3 measurements, and we'll know what side of the circuit has the problem. Let's put that into play. Start again, as we always do. Start at the battery. I got 12.14 volts at the battery. Next measurement, at the load. Positive side of the load as close as I can get. And what do we measure there? 12.04. Well, in that case, I've only lost 1/10 of a volt. 1/10 of a volt voltage drop from point A to point B. That's fine. That's all. I can explain that easily. I got the fuse, I got the wiring connectors, I got the splice points, I got the connection at the battery. I'm happy with that. Haven't found the problem though. So now we're going to move where? Ground side of the load. We'll go there. Look at that. 6.21 volts. I hope you can see that okay on the meter. I want to stress here exactly what this is telling us. All available voltage, all this stuff that's available up here in the battery is going to be used by the various sources of resistance in the circuit. We understand that, right? And we know that all of these little points along the way, the contacts in the switch, across the fuse, in the wiring connectors, at the battery connection, all of these are all sources of resistance that are going to take their fair share. Little bit, not much, like we saw on the positive side, 1/10 of a volt, all I wanted. If something unwanted shows up though, it's going to take its share. So when we see a reading like this, that should be an automatic red flag to you that something between here and here is saying, hey, light bulb, you're only going to get half. I want the other half. I'm waiting on the other half. And that's the problem. So this should be an automatic red flag. If you see voltage, when you measure, as we're measuring here, negative meter lead to the negative side of the battery, positive meter lead to the negative side of the load, and you see voltage, just like we did at the very beginning of this presentation, you automatically know that the fault lies between this point and this point. There is a source of resistance somewhere in the ground circuit. And that's also why it is critically important that you stay referenced to the battery, especially on the ground side. I don't care if you're in the trunk, make a meter lead that's long enough to reach. You must test the entire circuit path or you're gonna miss it, right? The ground side connects to the body, then the body connects to the block connects to the battery, and that's how you get your ground back to the battery. So you can't ground in the trunk when you're checking something in the back of the car and test the entire path back to the battery. You could have a bad connection, bad ground up there in the engine compartment, and you're going to miss it. You with me? Test the entire path. Now, all right, Pete, I got a problem. I know there's a resistance in the circuit. How am I going to find it? Well, the easiest thing to do is pick points along the circuit that are easy to get to first, and you're going to work your way back towards the battery. All right, so let's do that. And what we're going to look for, as we move back towards the battery is for that source of resistance, that unwanted guy, to consume his share. Because just like we saw in the descriptions and the charts I showed you earlier, all the voltage is going to be consumed by the sources of resistance. So when I get to the end of the line, I should have what left over? Very little, right? So that's what I'm looking for. I'm looking for that to change to next to nothing. All right, go here, still got it. Let's go up here, still got it. This one. Okay. Now that's more like it, 46 millivolts. That accounts for the resistance between these 2 points, normal. Happy with that. Meters return to normal. Now I know that the fault lies between where I'm at now and where I just was. And now I can start homing in little smaller chunks until I find exactly where that son of a gun is. You with me? That's how we find it. That's where we find that unwanted resistance. But I really want to stress to you, because this is the one that throws guys off the most. When you have your meter, as we did, 2 ground points, right? Or at least so we thought. We're not actually on 2 ground points, are we? Because somewhere down the line is another load, which means we're on the positive side of that unwanted resistance, that unwanted load. Got me? Very clear, very clear. I want to make sure you understand this. One confuses guys the most. All right? Let's move on. Okay, here's another example of not enough current getting to the load. It's dim. It's not working properly, if it's working at all, okay? If it's not getting enough current, why? What would cause the current to decrease in the circuit? Well, either the voltage dropped off or the resistance went up, right? That's what we're looking for. So we're going to do it just like always. 3 measurements. First one at the battery, 12.14. Now we're going to move that over to the positive side of the load. 5.92. Is that right? What should it be? It should be pretty darn close to the 12 point something that we just measured, right? It's not. It's only roughly half that. What does that mean? Well, that's all that's left over. I'm on the ground side of something over here. And it's taking half the voltage away before it even gets to my load. Do you understand that concept? It's vital that you understand this. If you want to be a good electrical troubleshooting, you got to nail this down and speak this language. What do we do to find the problem? Well, just like we did on the ground side, I'm going to start moving back towards the battery till my meter reading returns to normal. Either side of the fuse, nope. We'll come up here. Still bad. And then we'll come here. Well, big difference. All right, now we're back to battery voltage. What do you know? It's got to be between where I am and where I just was. And that's how you find the source of resistance on the positive side of the circuit. So how do I find this thief? I start moving my test lead back towards the battery, using easy to access checkpoints at first until my meter reading returns to normal. Once it does that, I know that I've passed where that thief is hiding, and I can start working my way back the other way, only this time in smaller increments, until I finally nail down exactly where that son of a gun is. And that, my friends, is voltage drop testing. Now, I encourage you to take what you've learned so far and put it to work. Take a battery, some wire, and a few light bulbs and build yourself a simple circuit. Take the time to measure the voltage or pressure differential at different points in the circuit and think about what the meter is trying to tell you. I guarantee you will have that aha moment. So what if I could make this even easier for you? When we were taking those three measurements, the first two went together, didn't they? We measured the source voltage, and then we would come down and measure the voltage at the positive side of the load. If we took 11.9 away from the 12.1, that 0.2 of a volt is the actual voltage drop between here and here. Very little. All right? The meter's doing the math, or we're doing the math instead of letting the meter do the math. So I'm going to show you how you can, here's a two-step voltage drop testing method that you can put to work tomorrow in your shop to help you isolate which side of the circuit the fault lies, and it goes like this. Rather than moving your positive lead off of the battery, we're going to take the negative lead and move that to the positive side of the load. Now the meter's doing the math. Now we're showing that between those two test points, there's only about 150 millivolts worth of drop. Remember what's measured between the meter leads? The electromotive potential, voltage, pressure, however you want to think of it. Have we lost any pressure between these 2 points? What's the difference in pressure between these 2 points? It's only 140 millivolts. So the difference in pressure here and here is negligible. I've got as much pressure here as I do here. You understand? That's why when we had our meter lead the other way, you could measure almost battery voltage here, because that's what you're measuring. There's 12 point something volts worth of pressure in the battery. That's what we're measuring. So when I'm looking for the amount of pressure between the two test leads and I'm seeing a really, really low number, that means I haven't lost any pressure between these two test points. You with me? So if I see that side of the circuit is just fine. And now to do step number 2. Now I'm going to move the negative lead back to the negative side of the battery, and now I'm going to use the positive lead just like we have been as the third measurement, and I'm going to measure on that side. If I see anything way outside of this reading, then I know that's the side of the circuit that has the problem. And that's the other thing I want to stress here in this section of the presentation. When you're looking for voltage drop, I've been asked numerous times, how much is too much? Depends on what it is. The more current the system would normally draw, the more allowable voltage drop I would include in testing that. For example, if I'm looking at computer-controlled circuits, I like to see them little, very small, few tenths, tops. But if I'm dealing with a starter motor, maybe a volt would be considered okay. But what I want to tell you is, regardless of what that minimum spec might be, when you have a problem with unwanted resistance in the circuit, it's not going to be a matter of a few tenths. It's going to stand out and grab you by the throat and say, I'm here. It's going to be up in your face that something's wrong. All right? So don't worry and quibble over a few tenths. Like I said, I measured a few tenths between these two sides of the load, between the battery and the load. Is that a problem? No, because all of this is accounting for that. If I see a huge difference, then I have a problem in that side of the circuit. Let's try a few simple examples. First, we test source voltage and get 12.41 volts. Now we move to the positive side of the load as close as we can get. Now keep in mind, the other meter lead is still referenced to the battery so that we can check the entire circuit path at one time. Here we measure 12.40 volts, a loss of only 10 millivolts. So that's not the problem, is it? Our next basic test is on the ground side. What do you see here? Well, we have a reading of 5.11 volts. So does that tell you what side of the circuit has the problem? What steps would you take next? What is the meter trying to tell you? Let's try another simple test. In this case, there's no backup lamp on the left side. Now, would you just swap out the bulb? Because if you did, you'd be wrong. It wouldn't fix this problem. Now, the first step, after we've checked the source voltage, is our measurement at the positive side of the load, as close as we can get. And notice here, we're reading a perfect 0. Didn't I tell you you would never read a perfect 0 on a circuit that was working properly? So what is this telling you? Do I need to even bother testing the ground side? So we're looking for the cause of this obviously open circuit. And what are the most likely areas to look for? How about where the harness is constantly being moved? Like here, between the trunk lid and the body of the car. Here's a measurement we're taking on the trunk lid side of the harness. Have we found the problem yet? Now we're going to move to a point on the other side of the trunk lid where it goes into the body. The reading on this side of the bend, 11.87 volts. Is that a normal reading? Maybe it's lower than we'd like to see. The battery, it's not the battery voltage, but we did see a huge change. So the issue has to be between this point and the last measurement point. And there you are. Now let's try to figure this one out. I could have fixed this one with my voltmeter, but not when using the first method I showed you. In this case, the lights were flickering when the car was running, so the source voltage was constantly changing. I needed to get the leads on the same side of the circuit, positive to positive and negative to negative, like the second method that I shared. So in this case, notice the green trace. That's the field coil of the alternator, and it's a ground side control. You can see that there's almost a volt difference in amplitude. Since it is a ground side control, the problem has to be on the ground side of the field coil circuit. Moving back towards the battery, here's what I found. Now, even though the cable connection had been cleaned, you have to remember corrosion can travel a long way, and it may not be sufficient to just clean the cable connection. In this case, it did not fix the car. How would we have found out? By verifying that repair, which obviously wasn't done. So what would you do if you can't access the load, or the load has more than one power and ground feed to it, like an ECU? Well, you use a substitute load. Take a look at this video clip and learn how. Whenever I'm asked for help troubleshooting an electrical problem, one of the first things that I ask the technician is, have you verified good power and grounds to the component that you're having a problem with? And 90% of the time, the answer is, yeah, Pete, I've got power and I've got good ground. But when I start asking a little more detail of how they tested power and ground, well, that's where I start to see where the problem lies. And I want to kind of clarify that. Let me demonstrate. Here we have a headlight circuit that's not working. I get a call, Pete, I've got a headlight circuit that's not working. One is, one's not. I put a new headlight in, it's still not working. Well, did you check power and ground? I sure did, Pete. Well, how did you check it? And this is not atypical of the kind of responses that I hear. Well, I grabbed my test light, Pete, and I hooked it up to the negative side of the battery. And then I disconnected the headlight rather. So we'll simulate that here. And then I took my trusty test light and I turned the key on and turned the headlight on, and then I hooked it up and got a nice bright test light. So I've got power. And then I moved my trusty little test lead over to the positive side of the battery. And I went to the ground side of that headlight switch, Pete. And again, I got a nice bright, see if I can get that in there so you can see it good. Got a nice bright test light. So I've got good ground. So I don't get it, Pete. Why is the headlight not working? Well, there's a couple of reasons for that. First, what are we really measuring when we just measured this side of the circuit with our test light? All we measured was open circuit voltage, didn't we? It was no different than if I'd gone across the battery itself. Now, had there been a problem, if it was severe enough, yeah, you might see it. Maybe the light bulb's a little bit dimmer than what it should be, but I don't know about you, but my eyes aren't that good. I can't quite tell a huge change in resistance just from the quality of the headlight or the test light bulb. The other factor that comes into play is just what kind of bulb do you have in your test light? It's going to impact with the resistance in the circuit. And I think you'll see that as we go along, and you'll understand a little more as we go along. So how should the technician have checked the power and grounds? Well, let me put the circuit back together and we'll talk about that. If you watched the trainer video last month, we covered some electrical fundamentals. One of the things that we stated in that video was that all electric circuits have resistance. The wire has resistance, the connectors have resistance, but the only true, really source of resistance should be the load, in this case our headlight. Yes, there's resistance in those little connectors. Yes, there's resistance in that section of wiring, but it's marginal compared to the resistance represented by the headlight. The second thing we talked about was how voltage is used in the circuit. The voltage is needed to overcome the resistance in that headlight, to get the electrons through that component, through that resistance. And we know that all the voltage supplied will be consumed by that resistance. So I should be able to measure close to battery voltage going in, but I should measure very little coming out if everything's working the way it should. That's the whole idea behind voltage drop. The third thing we learned was that if there is another source of resistance somewhere in the circuit, for whatever reason, that it's going to demand its fair share. And if that's the case, that's going to impact the readings that we get when we check against our load. So how should you test power and ground circuits? Using voltage drop to test their ability to deliver voltage to the load and provide a clean ground path from the load. So let's do that with our multimeter next. I'm going to set my multimeter on the voltage scale, and we're going to do it first in what I would call a traditional, conventional method. Something that's easy to understand if you're new to voltage drop. And I'm going to place the negative meter lead on the negative post of the battery. And then I'm going to measure how much voltage potential do I have to work with, or does the headlight have to work with. So we're going to measure that first. And we measure 12.40 volts. Okay? With everything connected and the circuit operating on, even though it doesn't look like it, I'm going to measure the voltage going in to the load. I'm not going to disconnect anything, but I'm going to get as close to the load as I can and measure the voltage there. Here I've got 12.34. Okay, that's not quite 12.40, is it? That's 0.06 or 60 millivolts difference between the battery and that point in the circuit. Well, remember what I said? All the sources of resistance are going to share that voltage supply. They're going to take their fair share. So what that's telling me is that the connector, the wire, the connector are all enough of a resistance to consume that 60 millivolts. Okay? But I have more than enough. That's marginal. I'm not worried about a small amount like that. So the positive side of the circuit's good. Let's check the ground side. Still have my meter attached to the negative side of the battery, but now I'm going to move my positive meter lead to the ground side of the load and measure the voltage present now. I'm measuring 12.24 volts. 12.24 volts. Well, that seems it's a violation of the rule that we talked about, isn't it? All the voltage supplied to the load, to the resistance, should be consumed with little or nothing left over. Well, I don't have a little or nothing left over. I got a lot left over. I got almost full system voltage left over, don't I? This is what often throws techs off. My meter leads are attached, ground at the battery and ground at the load. How in the world am I measuring voltage on that side of the circuit? All resistances in the circuit are going to take their fair share of the voltage. And it's not split up equally. It's based on the amount of resistance in proportion to the individual resistances, okay? What this is telling me is I've got a huge resistance between here and here, that's taking all the voltage away from the headlight. And that's why the headlight doesn't work, because there's a thief in the mix. All right. Let's try another testing method that you can use that makes it even easier to spot which side of the circuit has the problem. I'm going to do a little something different here now. I'm going to move my meter to the millivolt scale, and I'll tell you why. Most meters have a 300 to 500 millivolt ceiling. In other words, they won't read past that millivolt range. What they will do is give you like all dots, dashes, or OL or something like that that tells you you're over that measurable limit. What is the maximum allowable voltage drop in a circuit? For most general circuits, right around half a volt. Electrical circuits, a little less. High amperage circuits, like a starter, a little more. I don't want you to quibble over a few tenths though, okay? Like you just saw, if there's a thief in the mix, you're going to see it. You're not going to quibble over a few tenths. But by going on the millivolt scale and using the method I'm going to show you now, this is a go, no go decision, all right? Let me show you what I mean. We're going to go back and test just like we did before. I'm going to check the positive side of the circuit first, but this time I'm going to remember positive, positive. I'm going to place my negative meter lead on the positive post of the battery. So just remember, positive side of the circuit, positive side of the battery. What I'm doing here is letting the meter do the math. The meter measures potential between its leads. In the first go around, we started off measuring the battery voltage, and then we checked the amount of voltage present here. We got a 60 millivolt difference, didn't we? But we had to do the math. We had to subtract the 1234 we got here from the 1240 that we measured here. I ain't got time for that. I just want a quick answer. Is it good or not? So I'm just going to put my positive side of the circuit, negative meter lead positive, and then I'm going to measure the same way I did before, my positive lead at the positive side of the connector. And there you go. I've got 60.8 millivolts. 60.8 millivolts. That's 0.06 volts, right? So it's the same reading. It's the same result. And because it's not showing me OL or anything like that, I know I'm within my serviceable limits. I don't have a problem on the positive side of the circuit, or at least not up from this point to the battery, okay? That's another point you need to remember. I need to get this probe as close to that load as I can in order to test the entire path. Now we're going to apply the same concept to the ground side. Ground side, negative lead, ground side. Positive side, negative lead, positive side. Okay, got that? Okay. So ground side, negative lead, ground. Positive lead at the connector, ground. OL. And that's all I need to know. OL. Out of luck. Problems on this side of the circuit. It's between these two test points. So as I start working my way back towards the battery, as soon as that OL goes away, I know I've passed the point where I have a problem. But now I have truly tested power and grounds. And it really took no more time than doing it with that test light, only my results are a lot more accurate. Okay, I think now you understand the basics on how to properly test power and grounds on an electrical component. But what happens when we're dealing with a little more complex electrical component? You know, there are so many electronic control modules, little computers, that are on the vehicles today. It's vitally important that you first perform a valid power and ground test on these components before you pull the trigger and replace it. After all, like any other electrical component, if it's not getting a good clean source of voltage and it doesn't have a good clean path back to ground, it's not going to work the way it's supposed to. Now, the difference or the challenge becomes on these is that there's typically multiple power and ground sources. And unless you have a really good schematic or you have some engineering background, you may not necessarily know which ones go with which. Yes, you can test it like we did this example with the headlight by back probing the connectors with the ECM or the electronic control module powered up. But again, you have to test it under a variety of conditions, won't you? For example, on the ECM on the truck, we have to check it key off, engine off. We need to check it when we're engine is running, and we even need to check one of the circuits under cranking. But these are all things that you can determine when you're looking at the schematic drawing. And we're not sure which ground goes to what. So I may have my meter in the right place on the power side, but then I'm going to have to start going through all the grounds, and then it comes to be a little confusing, doesn't it? Here's a little easier way to do it. The first thing you're going to need is a substitute load, because the idea is to test the circuit integrity, all we really need is a load that's going to create current flow through the circuit, right? And if we have a load that's creating that current flow, we can perform a voltage drop on that load and still determine if there's a problem on either side, right? It's no different than what we just did on the board. In fact, I'm going to use the same component. All I did is I took a little headlight and I put some alligator clamps on one end, and then so we're going to need that. Of course, we're going to need our meter. And again, I'm going to use the millivolt scale just like we did on our test. We're going to do the positive to positive, negative to negative in order to determine what's each circuit path, whether we have a go or no-go issue. And then the next thing we're going to need, you're going to need a way to insert your meter leads into the connector for the module you want to test. And there's going to be different style of connectors, isn't there? You've already run into that situation. It's a test lead kit. And here's an example. This is one that's produced by the folks over at ASE Wave. It's got a lot more stuff than just the test leads, but there's one of the things I like about it is that there's a variety of sources or leads, for example, that allow me to back probe, or not back probe, but be able to remove the connector and insert the proper size pin into that connector, and then I can make my connection to my substitute load, and I'm not going to do any damage to the connector, okay? So we're going to use that as part of today's test too. The next thing we're going to need is we need to look at the schematic. We need to look at the schematic for, in this case, the engine management system, and we need to look at the pinouts for the ECM so we can identify the grounds and the power sources. And on the power sources, where's that power coming from? Under what conditions is that power source going to be powered up? Again, we have a fused battery wire, for example, on here that's key on, engine off, power all the time. But there's also a few other circuits that are going to require us to have the engine running and even cranking in order to check all of the power and ground sources to that module, all right? So now that we have that surmised what we're going to do, let's start with the first thing that I want to test. After I have the sources of power and ground identified on the schematic, I can look further into my service information system and I can find the pinouts for the connectors so that I can properly identify where I'm going to place my probes. Make sure that you follow the service information system. If they suggest that you disconnect the battery before you disconnect the control module, please do so. It's not unusual to have some type of, what's the word I'm looking for? You may have a spark across the terminals as you're disconnecting. That could create a voltage spike in the control module itself. May not cause a problem today, but it could cause an issue, a month, a year down the road from creating a hot spot on that circuit board. So that's just a precaution to take. Check your service information. Make sure you do, as always, the job the way it's supposed to be done. So I'm going to go ahead and get the camera a little closer now so I can show you what we're doing. And we'll show you how we're going to test the ground side first and why. All right, I've identified that one of the power supplies is fused battery voltage. In other words, there's power there all the time. Of course, on the engine control module, that's the keep alive memory. That's what keeps all the settings in place so they don't disappear on us when we shut the key off. That's pin, according to the pinout diagram, pin 96. That's this terminal here. And there are 5 grounds that we're going to test, starting here in the second row at pins 49, 50, 51, 52, and finally 53. And that's where we're going to start with this. Now why? Well, I know I've got fused battery here, so I don't have to worry about what condition the key is on. And if I can verify that all the grounds are okay, it's going to make checking the power side a little bit easier to understand. Now, the other thing that comes into play is that 99% of the time, it's a ground side issue that's causing your problem. It's not common for the problem to be on the positive side. You're going to find most of your issues ground side related. So we're going to go ahead and start with that. Now that I have these in place, I'm going to take my substitute load and I'm going to put it in place on positive to positive, and then I'm going to connect up the ground side. And now my headlight is lit. Now we'll go ahead and perform the voltage drop test. Okay, so now with the headlights hooked up, I'm going to go ahead and set the scale on millivolts. And now we're going to check the ground side. So remember, ground side, I'm going to check negative meter lead on the ground side of the battery, and my positive meter lead will go to the ground of the headlight load. So we're going to start off with the first. Right, there's that. 103 millivolts. Okay, that's only 1/10 of a volt, right? So we'll switch that over so you can see that a little easier. 1/10 of a volt. So that's okay. Not going to worry about that. And then all we're going to do now is go down the other grounds. Go to the next pin on this one. Measure that. 0.1. Number 3. 0.1. Number 4. 0.1. And finally, number 5. 0.1. Now I need to check the positive side. We just verified that all the ground side is all the grounds are okay, right? So we don't have any problem with those. So now we need to check to make sure that that B plus voltage is going to be correct. So I'm going to remove my lead down here at the bottom for the time being. Now we're going to just switch around like we did before. Remember, positive to positive when we're checking the positive side of the circuit. Move the negative meter lead over to the positive side of the battery. And now I'm going to move my positive meter lead to the B plus pin, or the positive side of the headlight load. Okay, 0.16. Now let me show you how I am actually measuring the load. Okay, so we're back to the load. Again, we're checking the positive side of the circuit, but what I want to point out here is I'm right here at the pin. Right? I'm right here at the pin. And I'm also, when I'm testing grounds, I'm right here at this pin. But Pete, you said you need to get as close to the load as possible. And those wires are going all the way up to the headlight. Well, let me show you what happens when we move there. Okay, I just want to make this as a point here. Right now I'm still set up to measure the positive side of the load, or the ground, or the positive side of the circuit rather. I'm going to leave it on the voltage scale, and I'm just going to go to, we're just going to find a spot to just kind of tap into the positive side of the circuit, and we'll see what kind of reading we get. Really close to the headlight. There you go, look at that. That's like 0.8 of a volt. That's kind of high. But what's the difference? I'm coming across this joint here. Let's talk about that a little bit. Let me just talk a little bit about what you just saw. That's a really good real-world example of something you might face in your bay when you start applying this technique. I told you when you're going to do a voltage drop test, you want to get as close to the load as possible so that you can test the entire path from power or to ground. And that's true. You want to do that. If I had started at the headlight, we would have measured almost a volt. That would have been enough for me to raise my eyebrows if I was suspecting a problem with the ECM itself. That may not be a clean enough ground for the low current circuits that the ECM contains. But what is our next step if we suspect there's a problem? We want to find that source of extra resistance. We start narrowing the distance, don't we, between where our meter leads are. So if I'm at the load and I'm trying to get to the battery, I'm going to start moving closer and closer to the battery until my meter reading returns to normal. The meter readings that we got right at that little connector splice were down to 1/10 of a volt. Is that a more normal reading? You bet it is. So where's the source of my extra 7/8 of a volt? It's in the section of wiring in my substitute load. Anywhere between the alligator clips I have on the end, to the splice joints I have here, to the pin connectors here. Somewhere in there is the source of that resistance, okay? I'm not worried about that though, because it's not a part of the ECM's normal path to ground. This is just a test device. So once I've eliminated, or once I've determined that this was the cause of the reading itself, I'm not worried about that. I got 1/10 of a volt down there, I'm fine. If I want to measure from there from the get-go, if you can access it, you can reach it, fine. Why did the resistance change on this? I can only think it's because of how hot it was getting. Headlight's hot, drawing a lot of current. This isn't exactly the heaviest gauge wiring. Maybe that's a solution for me. But I just want to point out that I don't care. This is a means to an end. And if I know that I have to move my way back to the load, if I go verify it right there at the connector where the true ground path for the ECM starts, and I see that I have no problem, I'm done. Well, I sure hope that you found this video presentation helpful. It's not going to matter though if you don't take the time to practice what you've learned. Review this video several times if need be until you make the material your own, and practice these steps I've shown you in the shop just the way that we did, just using some wire, a battery, and a couple of light bulbs, taking measurements here and there until finally it clicks. And when it does, you'll be the go-to tech in your shop for handling electrical concerns. Thanks for watching.